Now, I don't expect this to go viral anytime in the near future, so don't y'all worry about it.
It might, you never know.
You never know, that's true. You know, what inspires some people, you know, who knows?
Something like this, getting anywhere between $500,000 to $1 million
Assuming
easily.
these spots are going.
Go right ahead. Yeah, I mean, if you'd like to take one of those chairs back there, use them back there, wherever you feel comfortable sitting. I'm gonna probably be hanging out over, or mostly around here. Well, thank you all for joining us today, joining the museum for one of our presentations. Considering the weather outside, you could be doing a lot of things, but I appreciate you showing up here. As way of introduction, my name is Terry Panhorst. I worked at the Standard Hill Gold Mine, as you're going to see, for a number of years during the highlight of its production. I worked for 12 years in the mining industry, and then went back to school, actually in Reno, to get a doctorate in geology. And then for 20 years, I taught at the University of Mississippi. And in 2017, retired full-time out here to Boise. Climate is much better here than it is in Mississippi, guaranteed. So what I'm gonna do today, actually what you're getting is sort of like one of two lectures or more that I could do about Standard Hill. Today what I'm gonna do is focus on how the mining was done and how the mineral production came out of that, the mineral processing. In other words, how did we make gold? We have rock, how do we make gold out of that? So that's the focus of today. Another lecture I'll give at some point, maybe next year, we can schedule it. I'll focus just on the geology, and then I can bring in a bunch of samples. Sorry, no gold ingots, but I can bring in a bunch of samples so you can see what the material actually looks like in person that I'll be showing you pictures of. But today we're going to focus on the mining and mineral processing and a very light dusting over the geology of the situation. Okay, well, this is in California. When most people think about California, they think about the Mother Lode area, which is this sort of blob right in here on the western side of the Sierras. But as you can tell from this map, all of these little blobs represent gold-producing districts. And California actually produced gold historically out of a lot of different areas. What we're going to be looking at today is actually what's referred to as the Mojave mining district, which is down here in Kern County. It's about 100 miles north of the city of Los Angeles, for reference. So that's going to be the focus of where we're situated. The town of Mojave is just a few miles, in fact we'll see it in some of the photos, just a few miles outside of there. I don't know if any of you have been through the garden spot of Mojave on Highway 14. It's, most people don't stop. But it's right outside of town. It's easily visible from the town. And it's an old mining district. There were mines on Soledad Mountain and then some mines over here on what was called Middle Butte, historically over time. Let's zoom in a little bit more on the district itself. The Standard Hill mine, which is what I'm going to be focused on, is this group right up here. So you can see the town of Mojave up here. So we're not very far. We're just a few miles outside of town. This is the only project I ever worked on where I could leave the project site, drive into town, have lunch, drive back to the project site in about 30 minutes, all told. And that was taking a leisurely lunch. So it was pretty, it was kind of cushy in that respect. We'll see some images of Soledad Mountain, which sits here to the south. It's a much larger topographic feature. And it produced mostly silver with some gold in it. And then Middle Butte sits over here with its own collection of gold mines itself. Now our property, which I said was right up in here, if you look at the actual property, this is a more accurate sort of sketching of the map. This is Highway 14 over here on the east side. We actually produced out of 3 pits, shown here in the yellow, although everything kind of got blended together during the processing by and large. But the property that we had under lease was much larger than that, which we didn't really use, but that's how the lease works. This was all almost exclusively privately owned property, and so we had to get a lease from the lease owner, or from the property owner, to produce mine, and then the property owner got a share of the profits, so to speak. Well, the Standard Hill area is historically a fairly good producer for Southern California. It was originally found in 1894 by a prospector, and then rapidly developed after that. And this is what the area sort of looked like in about 1905, which was part of the heyday of the production from the Standard Hill. The largest mill, shown about 10 years later, grew substantially, so they were pumping a lot of ore through this operation. It was all underground mines at the time, high-grade underground sorts of mines. Now, what it looked like today, or when I first arrived on the property back in 1983, that's sort of what was left. You had a sprinkling of some structures here and there, lots of mine dumps and stuff, but it was basically, what appeared to be an abandoned mining area, which was why we were interested in it, because historically it had produced a lot of gold, and we wanted to take a closer look at that. Okay, none of the structures were still present, dotted around, that we had to sort of, they didn't get in our way, basically. We just left them there. So it wasn't an issue. Mostly an eyesore, and occasionally the landowner kind of considered them a little bit of a hazard in terms of, kids getting out there playing around and getting injured. But he didn't object if we knocked something down, because he just soon get rid of it. In addition, there was a bit of old equipment, like this old mine hoist. Most of the place had already been picked clean. Anything that could be scavenged over the decades was taken, up until the 1980s. Well, this is not something you can go out there and 3 guys can lift it up and put it in the back of a pickup, so that was something that was left. So that was where it was. We needed to move it, so we just got a dozer out there and kind of pushed it off to the side, and that worked. Something we did have to contend with, and you'll see some of that as we go through here, was some of the early mining activity. So there were a lot of old shafts and adits, structures coming to the surface that we had to be aware of, make sure we didn't get equipment in there, and fenced off so that it wouldn't be an issue of safety. Now, the old miners were interested in these fairly narrow, just a few feet wide, high-grade veins. And you can see from this image here, that was about the width of some of the veins. So they were coming in and mining this stuff because that's where the high grade was, that's where the good stuff was that they were particularly interested in. Anything that was around it, however, that was lower grade, they just left, because at the time it wasn't economic for them to get that. Well, that's, go forward about 80, 100 years, and that's the kind of stuff we're interested in now. Okay, so what is a vein? Well, a vein sort of is well shown in this picture of a pit wall by this dark zone that kind of comes off over here. That's the width of the vein. And so if we went up and sampled that, that's where the vast majority of the gold was located. There was some gold that was kind of sprinkled around in some of the surrounding rock here, but it really was relatively low grade or much less. And so, that's the kind of stuff they wouldn't, the old timers wouldn't mess with. But that was something we were certainly interested in.
Terry, I just want, when you say we, what was the name of the company? Or was
Oh, the company, well, it was actually a very tiny subsidiary of Shell Oil Company. It was Shell Mining Company, was who I worked for at the time. And like a lot of oil companies, during the early 1980s, they were interested because gold was, peaking out at several $100s an ounce, and so that was real exciting. And so they wanted to kind of get into that business and see if it made sense for them to pursue that. So there was a group of us, geologists and engineers, kind of working on this. Okay, this is what the ore actually looked like of the vein. Okay, most of what you saw there, that dark zone, is this brown calcite, which didn't have a whole lot of gold in it. Most of the gold was actually hosted in the quartz, but the calcite and the quartz were intermingled within the vein. So we just mined the whole thing, and occasionally you got some in some of the rock around it. Okay, so let's take a look now at the mining operation as it stood at about 1988. Okay, this is Soledad Mountain. Back here, this is the mining operation. These are our facilities, which I'll be walking through step by step as we go through this. But that'll give you a sense. We kind of got in there and rearranged the hill, so to speak, as some of the engineers used to describe it, and worked on that. Now, it doesn't look like that today, guaranteed. Actually, today, it looks a lot more like this. Now we're at that's Soledad Mountain, which has actually had a little bit of work done on it. Ours is pretty well closed up now. And we've added we didn't do it. All of this area out here has been added. Any idea what that is?
solar panels?
Solar panels. Yeah. So a nice flat area out there, so someone's come in and put enormous amounts of solar panels in there. So that's what it sort of looks like today. The pits have been somewhat filled in, reshaped, all this kind of stuff. But this is what we're going to be talking about. So we're going to go kind of back in time. I hate to say 30 years, it makes me feel old, but we're going back about 30 years to look at this operation to see. Now this is a standard hard rock type of mining situation, which means you've got solid rock in the ground that you need to manipulate in order to get the gold out of it. So the first thing you're going to have to do is do some blasting. All right, so in order to blast, you have to drill holes and put your explosive, your blasting agent in there. And so we would go out and drill pretty much a grid pattern about every 15 feet. And it would go down about 15 feet, a little bit more than 15 feet, because we were mining at the time in 15-foot levels as we worked through the hill. All right, so we work one at a time. Yeah.
What do you use for detonation?
You'll find out. Okay. After the holes are drilled, however, we need to survey the hole locations. And the reason we're doing that is because for each hole that we drill, particularly in the ore zones, we collect a sample, send it to the lab that was on site, so that we get an estimate of what the gold content at that location was. We use that to define where the economic gold zones are going to be and what's going to be the waste material around it. So we survey the blast hole locations, and then we start the process of the blasting. Okay, and to do that, what we used was ANFO, which is a very standard blasting agent used today. Okay, it's ammonium nitrate fertilizer, and fuel oil. Now, ammonium nitrate by itself and fuel oil by itself is reasonably stable. You can handle those things. You mishandle it, there's a problem. If you recall, about a year ago, there was an enormous explosion in Beirut, Lebanon, where I forget how many hundreds of people got killed. That was ammonium nitrate that was not properly stored and ignited, and it's a very explosive reaction. However, the ammonium nitrate we used was actually in these little balls. They're called Prep, and that's how it's produced. You can buy it in bags. We bought it in bulk, and so we actually had a truck that was filled with this stuff that would pump it into the holes for us. You drive the truck around and load each of the holes. So that was the blasting agent that we used. So as we finished drilling out a section, we got a section here that's been drilled out, and we want to blast that. This section here has already been blasted. You can tell that because the rock looks like it's been kind of poofed up. That's the whole idea. You just want to kind of poof the rock up, which breaks it down enough that the equipment can get in there and work on it. So as we finish drilling here, the blasting truck is brought up. This is where the Prel is. And so it goes around to each of the holes and pumps this stuff in. And as it's pumping in, it mixes the fuel oil with it. And so then you're pumping this slurry, in a sense. That's the blasting agent that is used. Now, and even in that state, that stuff is reasonably stable. You have to give it a real kick in order to initiate the ANFO. And to do that, you use what are referred to as boosters. Okay, Pentex is an example of a type of booster that can be used. But even the boosters are fairly stable. You need to give a kick to the booster to set it off. I mean, it's the safety aspect. All right, and to do that, that's where you use blasting kits. All right, so the cap is inserted into the booster, and then the booster is put into the hole, and then the ANFO is loaded on top of it. That's the process. Now the boosters come in different timings. They're in milliseconds. You don't want all your explosion force going off at the same time. All right? You don't get as efficient breakage. What you want to do is have it go off in a sequence so that you're always blasting toward what's called a free face. In other words, it's got a place to expand. And so you want to pop it off so it goes boom, 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 works its way back through the solid rock, but it's always got a place to kind of break apart. Heave, in other words. Like I said, these are only milliseconds, so if you watch a video of it, you can never see it. It all just looks like one big explosion. But in reality, over a matter of a few milliseconds, it's actually going off in that sort of sequence. So what you do then is, what was done here, there's the booster. The cap has been inserted into it. Then you tie it off, and the cap comes on this long cord here, basically, which you can lower into the hole. So it goes all the way down to the bottom of the hole. And then the truck would come by and pump in the ANFO. You only fill the hole about a third of the way full. Okay, and the reason for that is that you take all the extra rock bits down here, the so-called cuttings, and you shovel those in on top of the ANFO, because that helps keep the force of the explosion down into the rock. If you don't do that, if you don't put the stemming in, then what the ANFO will do when it explodes, all the force goes up the top of the hole, and you lose the effectiveness of it. Gives you a really lousy shot. It's what's referred to as rifling. And you don't want them rifling. You want the force to go into the rock and do the breakage. So for this particular shot that we're gonna look at here, we're getting everything ready. All the equipment, the drills and all that kind of stuff, it's all been moved off to a safe distance. And now the blasting crew is going in and tying all of the blast holes together with detonation cord, det cord. The det cord is what's actually set off. And it runs out here, and then that starts the sequence of the explosion that you see. But they're checking everything, so you can see how close we are to the highway. So you gotta be careful. We had to watch for the wind direction. You don't want it blowing over the highway, because if you create a big cloud of dust, shoot it over the highway, that's a recipe for disaster, so you didn't do that. So anyway, everything's wired together, and the head blaster, the licensed blaster, is off at a safe distance also. He initiates the det cord, which actually is done with a shotgun shell. He's got a little detonation chamber, basically, that the det cord goes into. You load it with a shotgun shell, close it, push the button. That initiates the det cord, which travels at like 20,000 feet per second, runs onto the shot, and everything starts, initiating, and away she goes. You can see the equipment's off over here, safe distance. That white that you see right there, that's part of the det cord. And then that's part of the initiation of the blast, and then more of the blast was up in there. In the particular section up for that photograph. Now, actually, every photograph I'm showing you is a slightly different blast, because we've had many dozens of them over the life of the mine. Sometimes we've got interesting little results, yeah.
Doctor, how far of a stretch of blast holes is that picture in the previous one?
You probably had about 50 in a row, and then 50 in this row, and then 50 in this row.
Well,
something like that, yeah. We find some old mine equipment sometimes during shots. We have to be aware of old mine cart. Also, there was a lot of iron, old rail from underground, nails, all that kind of stuff. You don't want to send that through the crusher, because that'll really mess things up. So, big objects we can catch in the pit and, toss those off to the side. Smaller objects like nails, there's actually a very strong magnet down at the processing plant that we're going to see that would catch all of that kind of stuff. So it doesn't go through the crusher. Okay, now remember that we surveyed all the blast holes and we took samples. So after a shot, you can lay out in map view, which is what I've done here, the different grades of ore that would be present, whether it's mineable, economic grade for us right now, or whether it's low grade stuff that we may hang on to run later. But you can designate it in map view and lay out then, okay, this is what we want to mine and send to the mill. This stuff, all this stuff out here goes to the waste dumps. That's how we know where the ore is versus where the waste itself is. Now, I'll point out ounces per ton is the way we categorized everything, measured things. Today, a lot more mines use grams per ton. Bless you. But ounces per ton, troy ounces per ton is what the designations refer to here. Now, I will point out that in reference back to the old timers, the red zones here, which is the highest grade, we could trace those from bench to bench. And they actually laid out ore chutes. So think of these things like this one here and this one here as chimneys of good fluid flow where a lot of the gold was brought up and deposited. And then outside of the chimneys, like in between here, it's lower grade material. Still economic for us, because we had to drill it and blast it anyway, and we had to move it, so we could still extract gold from it. The old timers weren't interested in that, they couldn't do that. And of course, they were all working underground, whereas we're doing all surface work. But back to my map that I showed you previously. Now we need to translate that information out to the pit so that the miners can know what to do with the rock. And so what was done was you laid out these ore zones, like right through here, on top of the pit, or excuse me, on top of the shot rock, and then we would put different colored pin flags in the material itself. So the loader operator, which is this fellow here, would recognize, oh, this is ore, this is high grade ore. Oh, this is low grade ore. Oh, this is waste. And so he would just load waste into the truck and then tell the truck, okay, now you go to the waste dump. Next one comes up, we're gonna load some more, you go to the mill. And so you could designate which way to send the truck. So it was all laid out on top so that one could see that. And what we used was a standard truck and shovel kind of operation, which is very common in mining back then, as well as it is today. Load the trucks and then instruct the driver where to take that particular load. And while he's out doing that, the next truck rolls up and you load that. So the trick was you always needed to have an empty truck sitting there ready for the loader to feed. So you always had to have some broken rock in front so that the process would be continuous. That was the goal. We wanted a continuous sort of process there. Occasionally, in real narrow zones, we had a track hoe that you could use to get real specific, digging out very narrow ore zones. That was much slower, but it was, necessary sometimes to keep the good grade that we were after for the mill. I hate lecturing with masks on. They're just, I may have to pull this down a little bit. It just doesn't work for me. I can go to the store fine with one, but not lecturing. Don't breathe on anybody. All right, I'm about ready to stop breathing now. Okay, anyway, where are we? Oh yeah, okay, we got the ore loaded. Now we're gonna haul it down to the mill, to the processing plant. Okay, because we gotta get the gold out of there, right? So trucks haul it down, and this is sort of an overview of the process, and we're gonna go through this very briefly to get back to some picture. Basically, we're mining the stuff, then we have to go through the process plant. That's what ore preparation means here. And then it gets stacked on a heap, which I'll explain how that works. We sprinkle it with cyanide solution, which goes through a recovery plant, and I'll explain all of this as we go along. But right now, we're sitting here, okay? We loaded up the truck, and it's gonna bring it down here for the preparation. All right, we got to get the rock ready to properly extract the gold from it with the cyanide. So this is our ore processing facility, all that we have right here. And back of it, this is the heap, which is built on a pad, and we'll talk a little bit about that whole thing too. But the ore comes down, gets dumped into a stockpile. A loader down here picks up a scoop and brings it over here to start the process of feeding it through. And basically what we've got is a size reduction going on here. We're taking it and we're crushing it down. Okay, so it'll be smaller and smaller and be more efficient when the cyanide hits it. Now the center or the heart of this whole thing is this screening plant. If you've ever been to a gravel operation, they have screening plants. What they do, okay? Where this was a double screen, so there's one screen right up here, and there's actually another screen down below. So the concept is after it goes through the primary crusher, It dumps onto this top screen. If it's not small enough to fall through the top screen, it rides its way all the way down and then dumps onto this conveyor and goes off to the left to go for some additional crushing in a secondary crusher. And then circles back around. If it's fine enough to drop through the bottom, onto the bottom screen, but doesn't pass the bottom screen, then it comes off over here, gets transferred over here to a tertiary crusher, even finer, which then circles back into here, and it goes through the cycle again until it can pass that bottom screen. That was the goal. Because that our metallurgical work suggested that was the optimum size we needed to crush down to. Well, this whole crushing process does create a lot of fine stuff that's actually a little too fine, all right, too small. And so to help with that, we use what's called an agglomerator, which is this large tube sitting on its side right here. Okay, the real fine grained stuff would have gold in it, but if you put it on the heap, it interferes with the cyanide percolation through the heap. And so what you want to do is kind of bind it up a little bit. And so the crushed ore that went through or into the agglomerator had a little cement added to it, just kind of a touch of cement, and then a little bit of water misted to it. And then this thing was turning the whole time. And so it would tend to ball up the really fine particles into these small balls and go out with the rest of the ore. So the whole purpose here was to help the permeability of the heap. So the cyanide solution would percolate down through it. So this is what the final product looks like, the ore that was crushed as it's going out to the heap. Our optimum size was a less than 3/8 inch size material. That's where if you crushed it finer than this, all right, you actually didn't get as good gold recovery for various reasons. And if you didn't crush small enough to this size, you left too much of the gold. And so it was that trade-off. It was sort of the best economics suggested less than 3/8 inch. So once we got it down to this size, from this point then, it goes out for stacking. We stacked it using what's called a radial arm stacker. This portion of it is telescoping. And so this thing could move, and it would just go back and forth, building the heap. And then this was all run with conveyors, and so when they kind of got through and kind of filled up, you took a section conveyor out, moved it back, and then let it continue going back and forth, building more of the heap. Okay, so at this point right now, we prepared the ore and we're putting it on the heap. All right, now the heap itself is built on a pad, so I'm going to walk through what's underneath the heap. That's really important. That's kind of critical to this thing before we get into exactly how the gold itself is recovered. So let's look at what's underneath the heap. In other words, what do you start with the pad? And inevitably, since we're working with cyanide solution, people get very worried about that. Last thing you want is cyanide solution escaping. You don't want to go into the groundwater, obviously. We don't want to lose it, because that's where the gold is. So, you don't want it just going off anywhere. You want to keep it controlled and flowing where you want it to do. So, sort of in cross-section, what you start with is go out and remove all the vegetation, and then you compact the soil very nicely, just like you do for any other sort of construction project. On top of that, the lower liner was a 40 mil, that's the thickness of it, 40 mil HDPE. And that may sound like a really weird abbreviation to you, but actually you're already familiar with HDPE, because that's number two plastic. All right, all of those kinds of containers, milk jugs, they're all made out of that number two plastic, high density polyethylene. The part we had was much thicker than that, than like containers you have there. But nonetheless, chemically, it's the same stuff. Number two is also used for piping, to make pipes, because it's a good strong sort of plastic. We used it, or they fabricated it in these large rolls that you could actually roll out. Stuff was stiff, but you could roll it out, because that's what makes for a good liner. In fact, HDPE is commonly used in all kinds of different construction projects, whether it be ponds, landfills, canals, anything of that nature, where you're trying to retain the water. It's a good impermeable surface to use, and this is typically how it gets delivered. And then you just take the rolls off of there, lay them out, and the different sections get welded together. Actually, a weld is they use this little spark generated little heater, and it actually melts the HDPE together in the big sheet. So then you have a continuous sheet. Okay, on top of the bottom liner, you put what's called a geonet, and a geonet is just a webbing to hold the upper liner apart from the lower liner. Well, why would we want to do that? Just in case any fluid, any of the cyanide got through the upper liner, it could then fall, it could then seep into this open space and flow out, and we could capture it. So the whole pad was built on a real slight incline, so any fluid was always going to be draining out in the direction that we knew, and we could capture that fluid, whether it was coming from the top of the upper liner, or if any got through and down to the lower liner. Okay, on top of the geonet then went a thicker layer of HDPE, so that's our upper liner. Same material, just thicker. On top of that, we put what's referred to as a geofabric, which is basically like an artificial fabric that's frequently used to cover and protect areas that you're going to fill with rock. Because you don't want rock puncturing the plastic, the HDPE, and so you put this geofabric down, and it provides just a little bit of cushion on there, kind of like what these guys. These aren't from the mine; those are just examples of other operations where they've been where it's been applied. Okay, on top of the geofabric now, we put out 3 feet of crushed ore, which is what the stacker's going to be sitting on. You know, if we had to go out there and walk on it, we don't want to be walking on that liner. We want to be walking on something that's more protective. So we pushed out 3 feet of the crushed ore, and then built the heap on top of that. So there's quite an engineering feat going on underneath the heap. We focus on the heap, but there's quite a bit going on underneath the whole thing. Now let me show you an actual picture of what's going on here. Okay, this is the area of the pad. Upper liner sits out here. Here the geofabric has been spread out. You can see how wide it is. Out in front of the protective layer, which is being pushed out in this section. Meanwhile, this portion of the heap over here has already been built. The stacker's here is finishing up this, and we've got this under leach, so that's why it kind of looks darker up there. It's damp, it's got the fluid being applied to it. So once this works its way all the way back, then we're going to bring the stacker and put it out over here and start building this next section of heap this way. And as the stacker gets through with what it's doing right here, pull out one of these conveyors, move the stacker back, and that just works its way back in that sense. And you can see it's on that particular interval, it's about halfway back now. Many fewer sections of conveyors right there, but we can go ahead and get that under leach as well as leaching some of the stuff back over here. Okay, by this point now, we've got the whole pad filled with that first level of crushed ore. Now, I like showing this picture because you can see all this white area here on top. You think, what the heck is that? It's actually ice, that's frost. Because this is January, and even Southern California can get cold out in the desert. So yes, it does get chilly down there. But it's, yeah, the cyanide solutions we were applying were kind of freezing there on the top. And you had to wait till the sun came up and sort of melted things to get the process going again. A minor inconvenience. Okay, well, we didn't stop there because we still had more ore that needed to be processed. So we put a second level right here now up on top under leach, and we even put a third little half level all the way up here. Looks like we're building a pyramid, doesn't it? But you know, you're going to use the whole area. That's one of the problems that they had. I was the geologist for a while in the project, and they gave me a drill rig and said, "Go find more ore." So I did. Yeah.
When you're leaching the heap, do you leach one level, then place something on top after getting done with the first one?
Well, we're not really done with it. It's not exhausted. It'll just have to continue leaching because whatever you apply on top, in theory, is going to percolate down through the whole heap. So the lower levels will still produce a small amount of gold, while we're producing more gold out of the upper levels.
How's it drain how's it drain out if you're stacking like that?
Oh, because there's no line or anything between the different levels. This is all from here all the way up to there. It's continuous crushed material. And so the cyanide put on top will percolate all the way down and come along the drains.
Oh, okay.
Yeah, so it's a continuous thing. All you're doing is just making it thicker.
I get it now.
Yeah.
What's your time frame? I mean, how long since, I guess since you started the pad?
Okay, we started the pad in 1987. All right. By this point, it's 1991. Okay, so within a few years, basically, we've got this. This is a fairly small operation by the grand scale of things, but it gives you a good idea of all the other stuff that goes on through the whole process. That's kind of the fun of working on this project. I learned so much about all these little bits and pieces that, you know, it's kind of like working for a small company or working for a big company. You know, you learn different things that way. Okay, once we got the pad loaded, got the heap built, we sprayed with cyanide solution. Okay, and actually, a lot of this is just agricultural technology that one uses. You lay pipes out there, you have rainbirds, and you pump the cyanide solution through, and it just you know, sprays it around, falls on the top of the heap, and then percolates in. Now, cyanide is actually a tricky substance to work with. All right, so you can't just dissolve it in water. All right, because it'll immediately gas off. That's why they use it in, you know, gas chambers. Because you drop it in acid, it goes to gas. You don't want it in gas. We want it to stay in solution. And so the fluid that we're pumping here is actually very alkaline. We have to keep the pH at about 10.5 to 11. And if you know anything about alkaline fluids, that's alkaline. You put your hand in that fluid, it's how caustic it is gonna hurt you a lot more than any cyanide. It was very caustic type of solution. Okay, anyway, right now what we've done is we built the heap, and the solution has come through. It's loaded with gold. So basically we're at this point now And now what we're gonna do is walk through this whole section here of how we're actually gonna recover the gold out of the cyanide. Now to do that, to help us understand that a little bit, I'm gonna use a different road map. This one's more specific to Standard Hill itself. So what we've got now is the heap. It flows through and out to the collection channel, which brings it down through the processing plant. Okay, 2 ponds of note, because I'll be talking about them as we go along. We have a pregnant solution pond. That's the solution that's coming off the heap. It's pregnant, why? It's loaded with gold and silver. Okay, this is the barren pond. No gold. Okay, well, I mean, these are mining engineers and processing guys that make the terminology up, you know, what can you say? So the idea is that we're gonna come down here, take this solution, pump it through the processing plant, and pump it back over to the barren solution, and then that goes back up on the heap, so it's recycled. So you just keep using that solution. And in reality, you have to add more to it all the time, but the solution keeps getting reused. Okay, in map view, this is give you a sense of scale. This is the pad that and the heap that we've been talking about. Pregnant pond and barren pond are over here. Our processing plant is actually a real tiny little thing. That's what this is. Office is set right here. So it's all sort of, you know, kind of a tight little operation. Oh, the other crusher, ore preparation all went on in this area. So it really wasn't a very big footprint. The heap was the largest aspect of the whole footprint. Okay, if you stood on the top of the heap and looked at all that, that's what we've got here. Okay, these are the collection channels which drained into the pregnant pond. Okay, which this fluid then got pumped through the processing plant, which we'll walk through, then discharged into the barren pond, and it comes back up to where I'm standing. So it's the closed circuit concept. You want to reuse all of that. Okay, so once we got it into the pregnant pond, what we need to do is run it through what's called a carbon absorption circuit. Okay, so that's what we're going to talk about first. How we get the gold off or out of the cyanide, and we actually put it onto carbon. That's in these columns. Okay, there's 4 columns right here, vertical columns. The solution is pumped into that, the pregnant solution is pumped into the carbon columns, and it overflows from the first column to the second column, overflows to the third column, then overflows to the fourth column. And the carbon is actually in the center portions of here. Okay? So as it's being pumped down to the bottom of the column, and then it, through hydrostatic pressure, then is pushed back up through the carbon before it overflows to the next column. And so we do 4 to try to extract as much gold out of the cyanide as possible. And it was very efficient system of doing it. So after we do this, now what we've got is the gold adhering to crushed carbon, basically. We used to actually, there were coconut shells. They were fired coconut shells. So they were roasted coconut shells. That's how you buy it in bulk from Sri Lanka. That's where we got it, you know. It's amazing, you know. Creative. Okay, from there, what we're going to do is have to concentrate it more. And we send it through this carbon elution, which is a fancy way of saying stripping cycle here. So we've got the carbon, we've got the gold on the carbon, but we need to strip it off of there. All right, and that's done in these tanks, which were right next to where the carbon columns were. So it's pumped into these tanks here, which are heated, and actually had very concentrated cyanide solution in them. So we pump the carbon into there, the very concentrated cyanide solution would yank the gold off of that carbon and put it back in solution. But now it's in a very concentrated solution. Okay? So the whole idea here was to rip it off that carbon, and then we could take that carbon, the carbon that had already been stripped, and put it back into the carbon tanks, those vertical column tanks, and reuse them again. Okay, so now we've got the gold in a very concentrated cyanide solution. So what do we do with it then? Well, we actually go to a little electrowinning process. So we need to put it in some sort of solid form. And to do that, we basically use the ancient science of electroplating. All right? This is an electrowinning cell. And in that cell, you had a whole series of these cages, these big cages like this, empty cages, which were loaded with steel wool. Okay? You lower the cage with the steel wool in it into this tank and put an electrical charge across the steel wool, pump that concentrated cyanide solution with the gold through there. Once the gold came into contact with that steel wool, got very excited because it would hold on to the steel wool because of the electrical charge. And so we basically be stripping it out of that concentrated cyanide solution and putting it onto steel wool. So at this point now, it's actually getting fairly concentrated that security becomes an issue. So this is where we had cameras and stuff like this for monitoring purposes. Prior to this, it wasn't concentrated enough to be of any interest to people. But at this point now it is. You grab a handful of that steel wool, you got a little bit of stuff there. That's kind of important. The steel wool now is what's used in our final step, which uses a gas furnace. Okay, because we want to get it off the steel wool and into a fairly concentrated form that we can then ship to a smelter. And so this gas furnace is not the kind you're going to find in your house or anything like that. I mean, this is an industrial size, small industrial size blast furnace in a sense, if you want to think about it that way. So inside the furnace there's a crucible. So old Lonnie, who's working here, he was the master alchemist. He would load the crucible up with the steel wool and a bunch of different fluxes, materials to help things melt at a lower temperature. Fire up the furnace, which would take hours. On days that Lonnie was going to pour, it was a long day for him. Okay, it would take hours for this to all go molten, but you got it up to like 2,400 degrees Fahrenheit. You're not going to do that in your oven at home either.
Was that deal due to the steel wool that was part of it?
Well, what you wanted to do is basically break everything down into its elements, and you could do that if you melted everything. So you wanted to keep the iron, which is in the steel wool, away from the gold, because you don't really want the iron, but you do want the gold and silver that came out of there. So this took hours just to melt everything, and then we had to take it out of the furnace. Now we did that using this little critter here, which is referred to as a witch's hat. And the reason they call that is because the thing was actually it looks like an inverted funnel. Okay, and it's got little legs which are kind of hard to see here. You'll get another picture of that. And we've got it on a cart which you can wheel right up. So when the batch is ready, when Lonnie says, okay, we're ready to pour, then it's poured into the witch's hat, and you can see that stuff is obviously very hot. I mean, that's molten metal right there. But it separates based on the density of the elements. So the gold is very heavy, it goes immediately to the bottom of the witch's hat. Silver also goes to the bottom, it's very heavy. All the iron and other stuff like that will sit on top of it. So after you make a pour into the witch's hat, you wait again. Because it takes hours for that thing to cool off. We used to joke that if anyone wanted to steal anything, we'd give them free rein. All you had to do was come in at this point and pick up the witch's hat with your bare hands, and you would have it. For some reason, nobody ever took us up on that. I don't understand it. So anyway, it took several hours for this, that little baby there to cool off to a point where, you know, it wasn't gonna burn through the floor of the shed. And then you just took it and tipped the witch's hat over. And what was left? At the very point of the witch's hat is something that looked like this. That's your gold and silver that came out of the pour. All right? And this is what's referred to as doré, which is that mixture of gold and silver. That then we shipped to a refinery, because we didn't have the capability on site to make, you know, what you all see as, you know, gold bars, for instance. Yeah.
After you tip it out of the witch's hat when it's solid, do you have to slice the iron away from
It kind of broke.
It just
When
kind
you
of...
tip, yeah, when you pushed it over, the flux, the slag, which is composed of the flux and the iron and all that kind of stuff, it almost kind of shattered. But the metal was always, you know, there at the base of the thing.
So the iron part would shatter and the doré would be, is it still there?
Yeah, doré is solid. I mean, you could take a hammer to those. They wouldn't break. They'd deform, but they wouldn't break. Yeah.
What's the witch's hat itself made out of?
It's a form of iron that's very high temperature. I think it was probably mixed with some titanium and other things. You know, extremely high temperature materials. Okay. Yeah.
I should have asked this earlier, but what's so special about cyanide that you would use it in terms of recovering the gold or binding with the gold?
It's the chemistry of the cyanide. Cyanide is actually a very reactive compound, and it does very nicely taking gold and silver, other metals too, copper. We had a spot of copper in there. It would pull out copper. It would also do some stuff that you don't want, like mercury and arsenic, but we didn't really have that, but other places did. But it would pull those out as well. So it would go in and kind of really extract those kinds of elements and bring it into solution. Whereas the other stuff, the other minerals and stuff that were in the rock, it wasn't interested in. It didn't mess with those. But it's got to have access to the gold itself. That's why if you've got a deposit where you've got a lot of, say, the gold is tied up in pyrite or in other sulfides, that's a non-starter. What you have to do is take the sulfides and oxidize them. Basically, you roast them to break down the sulfide, get rid of the sulfur, and then you can leach that stuff with cyanide, which is probably what they're going to do, like with stibnite, the stibnite mine, because it's got a lot of sulfide material in it. Cyanide leaching only works if all your ore, like ours, is already oxidized. Mother Nature took care of that for us over millions of years. It turned everything, got rid of all the pyrite for us, and left the gold. Yeah.
What would the approximate weight of gold and silver be in a button like that?
It varied from pour to pour, depending on what part of the heap you're leaching, where the ore came from, et cetera, et cetera. In general, that would probably be about 2/3 silver, 1/3 gold. You can kind of tell a little bit based on the color. You know, the more silver it was, that means it actually had more silver in it, had a more silver color. One of those would weigh 40, 50 pounds. Again, depending on the size of the pour, you know, the nature of the material in there. At the time, we were dealing with $400 an ounce gold. Okay, and so one of those would be worth, $20,000-$30,000.
Wow.
Expensive doorstops. But we actually took them into a local bank, a bank in Mojave, and we had a bunch of safety deposit boxes. So we take those, put them in a little cardboard box, basically. Take them into the bank, put them there, and we had enough of them, we call a Brinks truck, and the Brinks truck would come, load them up, and haul them to the refinery.
Wow.
Some mines, you know what they use? The post office.
The post
They
office.
use the post office.
Wow.
You know, you're like, why would you do that? It's all insured. So, you know, if it got ripped off in the process of being shipped by the post office, you got the insurance money. Either way, you got the money. So it didn't matter. Yeah.
So how much rock, base rock would it take to make that 40, 50 pounds?
Oh, my goodness. Well, look at it this way. We were dealing with high-grade stuff. We would be getting 1/10 of an ounce of gold per ton of rock. Okay? So think of it in those terms. You can see that we're talking many thousands and thousands of tons of rock to create one of those. You know, tens of thousands, depending on the size, of course. But that's what it would take.
That's practically dust particles.
Well, yeah. That's why a lot of the gold you couldn't really see very well. It wasn't visible gold, but it was in there because you could you know run the analysis on it. And the gold was there, and you could leach it out of there, but you can't visually see it. No. Okay, well, that's actually where I was stopping. So, any other questions? I realize I ran through this really fast,
No, it's good.
but it gives you an idea anyway. Yeah.
Yeah, when you find the deposit with the gold, does it usually have that brown?
The iron oxide kind of staining.
Yeah, that brown calcite.
It doesn't necessarily have the calcite. A lot of times it will have a little bit of iron staining associated with it because at least at one time there were sulfides in there. And during weathering, the sulfides break down, but the iron oxide is what stains the rock and leaves it there. And that gives you an idea of, oh, there may have been some sulfides in there. If you know sulfides were in the rock, sulfides are an indication of the right chemistry of fluids that have moved through the rock that might also be carrying gold and silver. And so that's why you'd be interested and want to get a sample of that rock. Yeah, so you have to look for indicators. It's not like the old days where you go out and pan, you know, and find nuggets and, oh yeah, okay. You know, so I'm going to follow it up this way and maybe I'll find the vein. Those days are long, long ago.
Oh no, yeah.
So you have to rely on other indicators. Yeah.
So over the long haul, you know, when you have the big heap and you keep on putting more and more layers on top of it, if you had enough ore, would you just eventually just start another heap and then?
Yeah, you'd have to put out more pad or something like that. We knew that we weren't going to be doing that there. So we just kind of added a couple extra levels on top, and that was it. But if you've got more, you could do that. Other places run it. It's more economic, and from a permitting standpoint, it makes more sense. What they'll do is they will come in and actually move the old heap, the exhausted heap. They'll take that stuff off of there and go dump it someplace, and then reuse that pad.
Oh,
That's a lot more expensive because you're having to handle that material. But in some cases, that makes more sense to do it that way. So that's always a possibility too, to do that.
And every time you add more layers on top of the heap, do you pretty much exhaust the previous layers before you start adding? Or is it just a continuous, you know, you just keep on building and
Well,
eventually?
yeah, love a waffle for you here. Well, it depends. You know, you gotta keep the ore coming, you know, because it's coming through the process plant,
Mhm.
and you can't just let it pile up into this huge thing that it's like, we gotta move this. So it's a trade-off between how fast the gold is dropping off in the cyanide solutions, you know, as they're coming off the heap, how much are we getting, versus when do we start putting new ore on, because we've got the supply of ore coming, and we've gotta do something with it. So it ultimately is a kind of a trade-off, it's a materials handling issue. So how are we gonna do this? And that's where your mineral processing guys and your mining engineers really have to, you know, have their ducks in a row and sort of know what's going on and how to schedule this thing out. And make sure you don't put yourself in a bind. Yes, sir.
After completion of the actual mining, how long did you continue leaching the pad before the return?
Saying it was done. I had actually left the company by the time it got to that point, but to the best of my knowledge, it seemed like it went on for maybe another 6 months.
That's all.
Yeah, and then it finally got low enough that it wasn't making economic sense to continue it. And so then to decommission the heap, what you have to do is flush it with fresh water. And so then it had to flush for many months. They just kept pumping fresh water up there and checking it as it's flowing out to see how much cyanide was still left in there. Because, you know, ultimately what it got down to is you're putting fresh water in, you want fresh water coming out. And so you have to, you know, decommission it by flushing that and that. Yeah.
At that point, how would you dispose of it?
Well, we didn't. I mean, all we did was reshape the heap and left it, because that's what the permit said we could do.
Oh, okay.
So we actually looked into, well, you know, it's already crushed. It would be beautiful stuff for construction sites. You know, you need fill material, something like that, but nobody would touch it. Oh, it's got cyanide.
Too afraid of it.
But it won't have cyanide.
I mean,
But nobody would touch it, just for the liability aspect. So, you know, there's really no market for it, unfortunately. If there was a market for it, we would have sold it. Yeah, and they could, you know, come in and take it at their leisure and use it.
might be able to use it for construction if it wasn't so.
Yeah, now we did sell, we actually had a little side business of crushed rock, because there was some, we weren't that far, you know, less than 100 miles from Los Angeles. And so there was some potential for market as they were building more and more homes, you know, construction material, class 2 base kind of stuff, used for roads and subdivisions and things. And so we actually had a side business on our waste rock. We would crush that and provided that to some of the local contractors that were building roads and stuff. It added a little byproduct, a little extra money.
It's a good case.
Other questions? Well, thank you all for coming.
Okay.